Howdy, everybody. Today we're going to be going through biotransformation and toxokinetics. Now, in previous lectures, we have gone through the fate and flow of toxins going through the body. And if you remember on our breakdown chart, we had the toxokinetic section where we're going to have all of the stages from exposure, absorption, transport and distribution to target cells, away from target cells. Part of that also includes excretion from the body. Then we had this whole section in the middle that we kind of jumped over. The idea of transformation. Now, biotransformation is where we're going to take the original molecule, toxin, whatever we are working with, and then expose it to all the enzymes in your body. Now, your body has a whole series of different enzymes which are set up to detoxify compounds. Because remember, even though we're focusing a lot on anthropogenic human-made toxins in this course, we also have all of the toxins that you have co-evolved with. And also remember that we're going to have all of those enzymes that are working on food, other molecules. And what this can end up doing is essentially either transforming the potential toxin into something that is ideally less toxic, conjugated, linked up to another molecule is conjugation. We'll get through that in a minute, so that we can excrete it from the body and clear it. But in some cases, we actually transform things into a more toxic metabolite. Then they're going to interact with the target molecules and eventually have the final effects. Now, another thing that we've been seeing again and again is as you guys probably recall from previous lectures, we had gone through this nanotox pulse chase experiment where we injected a very tiny nanotoxic particle directly into the blood of the rat. And then we observed where it went, to the organs, to the general carcass, and also excretion through feces and urine. What we hadn't really gone through was the different phases on this chart. The phase 1, where it's introduced into the organism and is transported without transformation of the compound, versus phase 2, where we are conjugating and interacting with molecules, and phase 3, kind of detoxification. And we saw that when you inject the toxin directly into the blood, of course, it immediately goes into the red representing blood. And then over time, it decreases as it moves to the target organs and the non-target organs. And we also see excretion increasing. And as we move into the later phases, we see greater amounts of excretion. And this is kind of a classic pattern. As your body attempts to work on the toxin and detoxify it, it's going to turn it into a form which is easier to excrete and remove from the body. This is especially going to be important for lipid-soluble compounds which are not able to be excreted elsewise. So how we're going to transform the potentially toxic compounds is using all of the enzymes in your body. Pretty much all of the changes are going to be enzyme mediated. There are a few examples where it's not, where it is the toxic molecules are interacting directly with things that are inorganic or with other things and conjugating. But in general, you're going to do everything with enzymes, just like everything else in your body. So really what we're looking at is we're going to modify the potentially toxic chemicals, usually using either specialized molecules that are attempting to detoxify and or eliminate, sequester, just get that toxic compound out of commission and get it out of the body. But also we're going to have a lot done by your normal metabolism. Now, if we're looking at different target organs, the most bioenergetically active tissues are going to be the ones that are going to effectively have more of the biotransformation occurring in there. So of course, your liver, you have something that gets absorbed by your intestines, goes through your HPV into your liver. So it's going to effectively get the first shot at any compound that is swallowed. And remember that most of the toxins that you have evolved to deal with are things that are eaten. You eat something that potentially has a toxic compound in it, your liver is going to get first shot at it. So we're going to see really high intensity activity in the liver. In the intestines, the kidneys, the lungs, also dealing with interactions with toxic compounds because of filtering in the kidneys. Lungs for inhaled toxins, you'll see medium levels. Then your testes, the skin, the rest of the body, pretty low because they're not as metabolically active and they are not processing food and other materials normally or processing waste like the kidneys are. So when we're looking at the biotransformations, we have to think about where the target organs are and how it's going to get changed. Now, if you guys recall, there are a ton of top different chemicals that we talked about that are hepatotoxic. They're effectively going to affect the liver. And one of the reasons why is biotransformation is greatest in the liver. Now, what type of enzymes we're going to use are either going to be normal digestive enzymes or a specialized set of detoxifying enzymes. Now, the thing to remember is that when we kind of went through in earlier freshman level classes, we talked about enzymes having substrate specificity, that their active site only fits one specific substrate. Now, this is one of those oversimplifying for general biology. Now, as you probably learned from biochemistry and other classes, there are going to be enzymes that work on groups of different compounds or are going to be a little bit more flexible than just having one target, one specific substrate that they can work on. Now, that kind of freshman level, like only one target thing, we call that absolute specificity. That basically is one and only one substrate can be run and only one type of reaction. Now, these are actually very unlikely to be used for biotransformation of toxins because they are very, very specific. Only if that toxin is something that you have evolved a way to detoxify it and you have a special enzyme to do it, would you have that kind of reaction. It's extremely rare that that's going to be used in biotransformation. It is much more likely that we're going to have something that works either on group or linkage specificity. Now, group specificity, we're going to look at functional groups. So it might work on one specific R group of a amino acid, or it may work on like methyl groups, phosphate groups, ethyl groups. It will affect any molecule that has that hanging off of the side. Or we can have what's called linkage specificity. Instead of grabbing onto a functional group, in this case, it's going to work based upon the different bond types. So effectively, what we're looking at isn't a perfect fit of the substrate in the active site. There is what I tend to refer to as slop. You can have these molecules fit into the different active sites and end up getting changed. Now, what this means is we can have kind of jack of all trades detoxifying enzymes that are going to be more adjustable and more useful for doing biotransformations. Now, I like this chart out of Katsune et al., and they have kind of the stages of modification and conjugation. So in this case, it is for a drug. And remember that drugs are just toxins. Good old Paracelsus, the only difference between a cure and a toxin is the dosage and also its activity. So we're going to have the absorption of the drug, and then we're going to have the two stages of metabolism. And they break it up into phase 1 and phase 2. If you guys are following along, and on that nanochase, they also had a phase 3, which is basically a second time at conjugation on it. Now, phase 1 is where we're going to modify the molecules with some kind of metabolic activity. And phase 2 is all going to be about conjugation, grouping the molecules together. Now, depending upon the toxin or the drug, You may go through all the stages or some of it. Now, certain compounds are biologically active in their native form. So the medication or the toxin is going to get consumed and is going to basically go through the body, start working on the molecules, go through all of the interactions, and then just get eliminated for it. Now, this is pretty common for things that are going to be simpler molecules, and they're not going to have a complicated structure that needs to get activated or changed. Now, the challenge with this from kind of a drug standpoint is you can't have any kind of delayed release. You're going to have a hard time maintaining those levels within the body because it's passing through unchanged. We actually can take advantage of this phase 1 and phase 2 in order to maintain more even levels within the body. So, for example, this straight through unchanged. Think of something like nitrous oxide. You breathe it in, it interacts with your neuromuscular and your other synaptic junctions, and you end up breathing it out. Unchanged, simple molecule, NO, effectively. Versus other compounds which are going to get modified more. So, for example, a lot of medications will effectively be modified by either enzymes or inorganic conditions within your body. So you take the medication, it goes into your stomach. Your stomach starts working on it with very low pH acidic conditions, which is then going to produce a compound that can get distributed through the rest of the body. You could also have it go into your enzymes, get worked on by metabolic enzymes, and the slow process of chemically modifying it means that you don't just get an instantaneous giant hit of the toxin or the medication that's fast in, fast out. It's going to build up slowly and then transport through the body slowly. So we'll actually take advantage of this interaction effect with phase 1 and phase 2 in order to design medications that can hang around at the body longer and also have them be targeted, where we can take advantage of the different metabolic enzymes in different parts of the body to effectively better target where the medication is working, that it only gets turned into an active form in the tissues that are most responsive to it. So we can go straight through, we can get modified. We also can have phase 1 where we modify the molecule, get completely skipped, but then we go into phase 2 where we conjugate the molecule, and in general, this is going to then become a molecule that we can then excrete. So even with compounds that are hard to excrete, stuff that is lipophilic, so fat-soluble things that you normally want to hang around in the body, if we can get them to go through all of these stages, we can make them more hydrophobic so we can eliminate them from the body. Now, phase 1. This is going to be where we modify the molecule directly. And it's going to be some of your classic reactions you've been learning about since freshman year. So, for example, hydrolysis. We can take a molecule that is larger, polymerized, especially if we're dealing with something that is a protein-based poison, and we can break those bonds. Now, especially when we are breaking down these compounds, remember that we can have reactive oxidative species forms, ROSs, especially if we're thinking about breaking down protein-like toxins. We can end up with reactive nitrogen species. So an enzyme that's going in and chopping apart that polypeptide may end up breaking off a reactive nitrogen species that was hanging there, basically waiting like a little explosive, ready to go off from hydrolysis. Now, we also can do classic oxidation and reduction. And remember, when we oxidize something, we are removing electrons, transferring them onto something else. Think about what your digestive system is doing. It's essentially stripping off all of those electrons so that we can power our good old electron transport chains, generate electricity or electromotive force, and end up generating ATP. So this is really, really common because your body is constantly doing it. And it can take molecules that are relatively toxic and start just making them into compounds that are less toxic. So like a lot of the hydrocarbons, just the things that are lipophilic, can get broken down by oxidation. Doing things like beta oxidation, just like you break down lipids, but instead of breaking them down into compounds that we can then throw into the citric acid cycle, we're going to potentially turn them into something that could be more toxic in a reactive species in some way, or detoxify them. And of course, if you can oxidize, you can also reduce. And we can use electrons that are already present in the cell because we've got a lot of NADH plus H plus and FADH2 that we can use basically as electron donors in order to detoxify our different compounds. Now, for a general toxicology course, I don't need you guys to memorize the whole list of different ways that you can interact and reduce molecules, but you should be familiar with a lot of these terms just from general chemistry classes. So things like dehalogenation, we're going to remove a halogen group, remove a chloride, remove a fluoride, something like that. We can also break down disulfides. Think about disulfide bonds that are very common in proteins, so breaking disulfide bridges. We can affect nitro groups or N-oxide groups. We can break down sulfosides. The whole idea is we're going to end up adding electrons to break bonds or modify the molecule slightly. Now, azo reductions, I do want you to know about because they're extremely common, and we can take advantage of these for drug development and delaying release until we get into the correct target cells. So for example, a azo group, an N double bonded to N with two R groups hanging off the end. We can take this and use it to transport a molecule from a stable form that you're able to take orally, get it through the stomach, where it could be negatively affected if it was in the active form, the sulfonamide that we want to have, where we could end up basically breaking it down because of the acidic conditions. But instead, we can make a stable molecule. In this case, it's prontosyl sulfa, and then use azo reduction to break it up into the active sulfonamide. Now, you guys might have heard of sulfonamide before because it is a sulfa drug. It is one of our first antibacterial medications. And unfortunately, it does a great job at killing bacteria, but also other cells too. So we don't use this too much anymore, but we do use it in certain situations where we have drug-resistant bacteria, especially with things like MRSA, the multi-drug resistant Staphylococcus aureus, which for you guys who have been working in hospitals is what you're really worried that you're going to get your patients infected with. So classic removal. We also can do other changes. So for example, nitrobenzene, which is relatively toxic and can disrupt cellular structure. Well, we can reduce it, and basically just by changing it from an NO2 to an NaH, we turn it into alanine, which is a non-toxic compound. So the whole idea is we can take things and turn them into either biologically active forms that we want for medications, or we can detoxify them by essentially changing what the electrons are and donating them from things like NADPH reductase or free hydrogens with the protons that we can do the exchanges on. Now, oxidation types. Oxidation is going to be really, really common because most of the reactions that your body is doing to process food are oxidation. And again, do not memorize the whole list. This is something that if you guys go on into grad school, yes, for your PhD comprehensive exams, they will probably make you memorize all of these and exactly what they do. But at this point, for an intro talks, don't worry too much about it. But just think you can probably figure out what is happening just by the names of them. So, alcohol dehydrogenation. We're taking an alcohol and we're going to remove a hydrogen from it and oxidize it. We're going to take aldehyde compounds or alkyl compounds. We could have aromatic rings that we strip off. We can remove amine groups, NH groups from it. We can remove sulfur groups. We can dealkanize it, so on and so on and so on. We're just essentially going to take away electrons and modify the molecule. That's really it. Now, the compounds that are going to do these oxidizers, some of them are going to be part of your normal digestive processes. And they either toxify or activate a molecule basically by mistaken identity. And there are a number of toxins which effectively just get broken down by oxidizers into an active or toxic form, just basically as a mistake. But you also have a large number of compounds which are set up to detoxify things. So for example, alcohol dehydrogenase, ADH, is effectively breaking down alcohol compounds in your body. Now, alcohol is a toxin that organisms have evolved with since we had most metabolic pathways. Because remember, if we only partially break down sugars and ferment them, we're going to generate alcohol. Now, you guys, as mammals, do not generate endogenous alcohol, except very rarely where it is basically a partial fermentation in your gut in a more anaerobic condition, but your cells aren't doing it. You guys do lactic acid fermentation when you start running low on energy, but other organisms have the ability to generate endogenous alcohol. So for example, if your goldfish starts running low on oxygen, it will go into anaerobic respiration and it will do alcohol, ethanol generation instead of lactic acid. Now, the advantage is you do get more energy out of generating ethanol instead of lactic acid, but you do have the issue of the fact that it is a compound that can cause intoxication. So remember, it's going to affect your GABA pathways. And I always think about this as if you're really, really stressed and you're like running away because you're about to get eaten by a mountain lion or a bear, you don't want to end up making yourself drunk. So you don't want to turn around and go, "Ooh, pretty teddy bear, I'll play with it." So you guys have evolved the ability to generate lactic acid, which itself is acidic and directly toxic and takes more energy to generate. But just remember, you're inner fish. You guys still have all the pathways to end up breaking down all of the alcohols. Now, the other thing to remember about this is think about why fish could get away with having the generation of alcohols endogenously. They're leaky. Lots of flow in, flow out because they're living in the water. So always don't forget about it's not just the transformations, it's also how fast you're going to get them out of the body. So you've got a whole bunch of dehydrogenases. ADH is just one example of it. We're also going to have a lot of MAOs, monoamine oxidases. Now, these are going to be bound to a lot of membranes, especially the mitochondrial membranes, your cell membranes, and they are, in part, set up to break down compounds that could potentially be toxic, and some of them also to start breaking down more complex foods, especially things that could be burned for energy, but have kind of complicated structures that would not normally be bioavailable. So things like humic and fulvic acids that are more refractory. So think of these as multi-purpose enzymes, and they're going to essentially be group specific or linkage specific, and they're able to break things down. Now, again, remember your body is conservative evolutionary wise. So we usually have some other job that these ended up evolving for, and now they are able to kind of work and be useful for other factors. So for example, the number of the MAOs are actually derived from things that are set up to break down neurotransmitters. Because remember, when you release your neurotransmitters, you only want them present in your synaptic cleft for a very short period of time. So we're going to break them down. Now, these same compounds are also going to be useful for breaking down other toxins. Now, one of the kind of classic multi-substrate oxidizers that you should definitely know about is cytochrome P450. Now, cytochrome P450 is going to get bound to a number of membranes, and it is essentially going to act as kind of a temporary electron sink. So it can get used for oxidation and then also for reduction to effectively transfer electrons back and forth. Now, cytochrome P450 is essentially like the Swiss Army knife of your metabolic system. It can work on a ton of different compounds, and it is responsible for a large number of those transformations, either directly or acting as a coenzyme working with other enzymes to go through all those oxidation and reduction pathways. So it is incredibly important. Now, the text goes into a lot more detail on this, but again, at the general level, just remember cytochrome P450 is going to be one of the most important ones that you guys are going to have. Now, we can go through a number of different oxidation pathways. And one of the ones that I'm going to go through is the idea of alcohol dehydrogenation, because this is a classic on it. So in this case, we have our cell membrane where what we've got is ethanol coming through, and we're going to go through a series of detoxification steps. So the first thing, that ADH, that alcohol dehydrogenase, this is going to convert the ethanol into acetaldehyde. So we're going from ethanol, and we are going to effectively take NAD, use alcohol dehydrogenase, and transfer the electrons and the associated protons over onto NADH to generate NADH plus H plus. Now, of course, with this, we can use it for donating electrons elsewhere. We can also take those electrons, throw them onto the electron transport chain in the mitochondria and get some energy from it. Then we're going to have a second oxidation stage where we're going to have acetaldehyde get converted into acetate. And this is going to further detoxify the compound. And then we're going to have another pathway. We're going to use another enzyme to eventually generate acetyl-CoA from it. The same acetyl-CoA that we can just chuck into the citric acid cycle, the Krebs cycle, and generate NADH, FADH, a little bit of GTP. We can use it for energy. So the whole idea is it's usually not just one enzyme. It is a pathway to break down the compounds, ideally in this kind of situation where we're breaking it down into things that we can then harvest for energy, which is why we can actually get quite a bit of the energy from ethanol into your cells and take it from a form where it would normally have a cell signaling effect and it could affect your GABA pathways into something that effectively is just food, which is pretty cool. Now, remember that with these compounds and the enzymes, we're not going to have absolute specificity. We can have group specificity, or we can have bond type specificity. So normally, we would have that ethanol be worked on by the ADH, go through that nice breakdown pathway. But if we have other substrates, the biochemical pathways can get a bit confused. So in this case, we're going to, instead of having ethanol, have methanol, wood alcohol. Now, the methanol, when it gets worked on by alcohol dehydrogenase, it does not actually become the nice acetate and then get burned down. Your alcohol dehydrogenase will actually convert it into formaldehyde. Yes, the same formaldehyde that we use for preserving specimens. Yes, one of the major processes or major compounds that we use in embalming fluid. It is very, very toxic, and it will kill pretty much everything, which is why we can use it to preserve specimens. Now, formaldehyde on its own isn't really that toxic in its raw form. When it gets worked on by catalases and other dehydrogenases, we're going to end up turning it into formic acid, which is really acidic. It is also going to be toxic on its own, and it can damage a number of different structures. And getting rid of it is pretty hard. Unfortunately, the way to get rid of it is you've got to essentially conjugate it with folate and then be able to break it down some more. It's a longer pathway to get rid of it. So effectively, you can end up making an extremely toxic compound. Now, methanol itself will affect and cause intoxication, just like ethanol will. But more important, we're going to see the acid effect itself. We can end up with acidosis generally in the body, but we're also going to see a lot of ocular toxicity. Now, this is one of the kind of poisoning things that we've seen in the past. If you end up, when you're trying to make ethanol and effectively doing it from grains and, well, making whiskey and other compounds, especially once things that are distilled spirits, so at higher concentrations, if you end up with contamination from sugars that become methanol instead of ethanol, you can end up with a toxic compound forming. You make the formaldehyde, you make the formic acid, and you go blind. This is where the old wives' tale about all of the moonshine and other compounds effectively making you go blind. You know, don't drink that stuff, you'll go blind. That's because of this methanol toxicity becoming formaldehyde, becoming formic acid, damaging optic nerves. So even though it's kind of a, urban legend, old wives' tale thing, there is some truth in it. And usually by accidental contamination. However, there's another substrate which has been intentionally added to compounds or added to wines and other things, and it has also a really nasty effect. And this is ethylene glycol. Now, ethylene glycol you might have heard of before because it is used along with propylene glycol as an antifreeze. So in your car, your coolant, the reason why it doesn't freeze on a cold day is it's got ethylene glycol compounds, which has pretty cool colligative properties to prevent ice formation. Now, again, your body can mistake this for the regular ethanol and attempt to break it down. So in this case, alcohol dehydrogenase does its job, strips the electrons off. We get our good old NADH plus H plus. But instead of making the acetate, we make glyceraldehyde, which then becomes glycolic acid, that then we can end up turning through multiple transformations into oxalic acid, wood bleach. Now, that's going to cause damage to your cells. It also is going to be another ocular toxin and can make you go blind. Now, there's multiple pathways, as you see here. We could make oxalic acid. We also could make glycine, an amino acid that we can just use as a building block. And this is a cool example of multiple endpoints, where depending upon what enzymes are active at the time, we could have pathways that are either going back and forth, or we could have things that basically go to a non-toxic form or to a toxic form of it. Now, ethylene glycol toxicity shows up every once in a while. Not so much now that we have really good food testing, but one of the things that this compound does is if you look at it, it has a whole bunch of hydrogens hanging off the end, kind of like a sugar. So it can activate the sugar sensors in your mouth and be detected as extremely sweet. Now, this was added in some cases to make things sweeter. So if you've got wine that is, instead of being nice and sweet and other things, I'm not a wine drinker, so I don't really have a palate for it and could tell you all of the nuances, but people can. But just think about if you've ever had something that tastes a little bit vinegary. Because remember, vinegar and wine are very closely related. Just did you work on it with lactobacter or with regular yeasts. So if you have something that's got a little bit of vinegary taste, you can cover it up with sweetness. And there have been times where people have added ethylene glycol to mask the flavor of the wine, which then does lead toward this cheap wine causing people to go blind when they overdo it. Now, this is really rare because we do a lot of food testing now. Most of the poisonings that we actually see from ethylene glycol and propylene glycol that works in the same fashion is from animals consuming it. It's one of the reasons why with coolant, you always want to worry about leaking coolant. It's why if there's a puddle under a car that's kind of that greenish, pinkish, or other coolant color, you are going to not want to have your dog look at it. And unfortunately, dogs, because it tastes sweet, like super sugary water, they will drink it. And you end up with animal toxicity being the most common poisoning that you have from it. Children also, if they just haven't thought through things. Now, that's mainly the whole idea of the phase 1, where we're going to do oxidation, reduction, and hydrolysis. And this is going to end up generating a changed compound that usually, if it is something that's lipophilic, will increase in the amount of hydrophilicity and excretability. And we can end up with all of those different compounds being formed basically by modifying the molecule. Now, getting into stage 2, this is going to be where we're going to do some kind of biosynthesis or very commonly conjugation on it. And this is going to end up modifying the molecule even more, making it usually more excretable, but also can turn it into an active form. So for example, codeine. Codeine is commonly used as an opiated painkiller, used in things like Tylenol 3, and it is very effective at delivering very low dosages of opiates, which is why it is used more commonly for low-level pain, because the abuse potential is a lot lower. Because remember, so we've gone through with the idea of tolerance, you are much less likely to end up with tolerance and addiction if you don't have big spikes up and down in opiate levels. So in this case, the codeine molecule can actually go through 2 phase 1 different pathways. It could get demethylized and turn into norcodeine, which is going to be effectively just excreted from the body. So some of it's going to get lost basically to an inactive form. And from a medication standpoint, this is a bad thing. You're losing some of the efficaciousness of the medication. But if we end up going and becoming the other pathway, and it becomes codeine glucuronide, it can then end up going through another phase 1 stage after it has been conjugated and get turned into morphine itself, that then of course can go through a conjugation and then get turned into an inactive form, the morphine glucuronide, which will end up getting out of your body. Now, here's the trick. We can use this for time delay and to build up a low level of the active compound. Well, we really want to block the pain, the morphine itself, by having that transformation, because it has to go through the phase 1 biotransformation in order to become the active form. This is going to take some time. So what it means is you can have someone take a codeine pill. It's going to delay as it goes through the gut. You're also usually going to mix it with other compounds, so it's kind of pre-conjugated, that you're going to wrap it in compounds that your digestive enzymes have to break it away so that you're not getting a big pulse right away of the codeine. Then when it goes into your liver, it's going to get biotransformed, either detoxified or turned into the precursor molecule of the active form that then gets changed into the morphine itself. So what we end up with is, instead of a big dose of morphine all at once, which could have, well, risks for abuse, we end up with a low level being generated throughout the body. It also means that the medication is going to effectively have a longer duration, and you're not going to have people take it as often. So for low-level pain, this is why codeine is still a go-to because of this slow release effect. Now, do you want to talk a little bit about that whole cytochrome P450? Because it is going to be kind of that jack of all trades, because it can transform a number of different compounds. So we're actually going to take advantage of this for effectively delaying the release of medications or turning medications from a form that is stable to be swallowed and pass through your stomach and intestines into the active form. Now, the thing to remember about cytochrome P450 is it's going to have an iron compound to it. And iron is awesome because it has so many different redox states that it can be in. So we can essentially, by the assistance of cytochrome P450 and other enzymes, essentially set up a whole series of biochemical cycles involving reduction and oxidation at different stages. And especially if we combine it with other enzymes like P450 reductase, we can break down a large number of compounds. So the thing about cytochrome P450 is it's going to be kind of your Swiss Army knife. It's a tool, but you do need to have other enzymes in order to assist it and direct it. So don't think of it as something that's going to work on its own. It is an assisting molecule. It's basically going to act as a coenzyme. And a lot of the phase 1 pathways are going to use cytochrome P450 because we can change the redox states, we can steal electrons, we can donate electrons, making it super duper useful as essentially a temporary electron sink and something where we can change its electronegativity depending upon conditions within the body. Now that we're through phase 1, thing to remember is phase 1 can be multiple stages. Phase 2 is going to be where we take that multi-stage modified molecule and we bind it to something else. And the idea is to effectively generate a larger molecule that is going to be excretable. So the whole idea is, once we get through phase 1, a lot of times we're in kind of the middle of the biochemical cycles or the middle of the pathway, and it's pretty common that some of those are going to be very reactive. They're going to effectively want to have some kind of interaction with molecules. They might be a reactive nitrogen species or oxygen species. So think of it as we're at kind of a very high free energy level, or we've got something that is really going to want to react with your molecules. So the idea would be, let's grab on to those reactive groups like an amino group or hydroxyl group and bind it up so that we can react it, but react it in a known way that ideally gets it hydrophilic enough that we can excrete it. Now, there's a whole bunch of different forms that we can use, but some of the most common ones are glucuronide, where we can take something like glutathione, hook it to a toxin, and end up with the help of an enzyme, generate something like this glutamine sulfa conjugate that can get eliminated. We're also going to use a ton of different sulfate groups because sulfur, again, can form very strong bonds like disulfide bonds. We also are going to use a number of different amino acids, gluthanones, and methylation. Again, I don't need you guys to memorize these, but just think. We're going to now, after modifying a molecule, usually breaking it down into something smaller in phase 1, the idea is now put it back together with something else to turn it into an inactive form or to make it more excretable. Now, do remember that this is also going to be useful for medications because we can use that conjugation to slow down the delivery or even turn it into a more active form. Think of the codeine example from a couple of slides before. Now, glucuronide, I do want you to know the name of the two that in red. I'm going to test you guys on those. And this is really common. So it's the idea of using something that's a glucose-like compound to increase hydrophilicity. So in this case, we're going to take that alanine, which was moderately toxic. And remember from phase 1, we could effectively generate this alanine compound. And on its own, that is less toxic than the benzoalanine that it came from. But we still need to get rid of it from the body. So in this case, we're going to use a enzyme, glucuroneal transferase, where it's basically going to transfer a glucuroneal onto it. And we'll add a sugar-like compound, make gluconic acid, linked up to the alanine, and then this will be able to be excreted from the body. So really common to use sugar-like compounds, also common to use compounds from amino acids, and especially from parts of amino acids that are sulfur-bearing compounds. So for example, the processing of acetaminophen. Acetaminophen is a very common non-steroidal anti-inflammatory drug. It's Tylenol, effectively, or paracetamol is the other brand name for it. And it is able to interact with your cells only in the active form of acetamin sulfate. Acetamin on its own is not going to be reactive. But the cool thing about it is it's a very stable, non-reactive molecule, which makes it a good medication. You don't want to have something that is a super reactive molecule that is likely to oxidize on its own. It wouldn't last very long in a jar. Think about if you look at the different expiration dates on medications. An ideal medication is one that has a really long expiration date. So you want to make a stable molecule so that it lasts a long time. You also want to make it stable so that it doesn't react as it's going through your intestinal tract. It's got to make it through the initial enzymes in your mouth and your upper GI, and then make it through the enzymes in your intestines, and ideally only get changed where it's needed. So in this case, we can have this inactive form become active when we essentially interact it with what's known as PAPs, phenylhydrazine phosphosulfate. Complicated looking molecule, but this is going to be essentially a carrier for a sulfa group hanging off the end. So in this case, we can make this stuff basically by taking sulfate, a couple of ATP molecules, and end up making PAPs. So very easy to make and a high energy compound. Lots of free energy, highly reactive. Then we can use an enzyme like sulfokinase in order to combine that substrate like acetaminophen with the PAPs and generate the sulfated substrate plus a unloaded now PAP, basically taking the sulfate group, transferring it over, replacing that sulfate group with the hydrogen we stole from the other molecule and basically did a little switcheroo, and we can then just recharge this thing. So think of it as it looks a lot like ATP, having the core of it on there, effectively working like ATP to transfer high energy molecules. But in this case, instead of carrying phosphates, it's going to carry the sulfate that we can use for conjugation. Now, the cool thing about this is we can take this stable molecule, we can turn it into this active form that is also now more excretable. So as this gets biotransformed, it's going to interact with the target molecules, block the pain pathways, reduce inflammation, exactly what we want the drug to do. But then it's going to be excretable and you're going to be able to get it out of the body so you don't have to worry about it building up long term. So again, we can take advantage of these natural processes where we've got something like the NSAIDs and use those pathways to conjugate it to turn it into an active form. And depending upon what type of compound, it is going to effectively either be, sulfated, we could have it chlorinated, we could just have it go through phase 1 and have it link up to a hydroxide compound, and it is going to effectively do its job and then end up getting excreted out. So pretty much they are wonderful drugs because they can pass through the intestinal tract. have high utility once they've gone through phase 1 and phase 2. Phase 1 where things like cytochrome P450 is working on it, phase 2 with the conjugation, and then get excreted away. Now, the challenge is, though, this assumes that everything is happening according to the standard biochemical pathways. There can be interactions with other compounds. So, for example, most NSAIDs are counterindicated with the use of alcohol. You're not supposed to have more than 3 standard drinks per day while consuming NSAIDs because it can lead to hepatotoxicity, kidney toxicity, because these pathways can get interfered with. So just remember, this is where we end up with polydrug, polytoxin interactions, and something that on its own would not cause issues. But if we go down a alternative pathway, we can end up generating a toxic compound instead of the useful, normal drug compound itself. Now, this is one of the pathways for it. Looks pretty complicated, but acetaminophen, not a very complex molecule. And normally, it should effectively go through the pathways of either sulfonation or glucuronation. So it can become a non-toxic sulfate that's also active. It can become linked up to a glucuronide molecule, so basically either get sulfur added to it or a sugar-like molecule added to it. And it can end up then being removed from the body. But in certain cases, we're going to have it go down a pathway where it is going to be worked on by a few different enzymes that are normal digestive enzymes. And don't worry about, CYP2E1 and A4, but just realize digestive enzymes normally in all of your cells, in your liver cells especially. And in this case, instead of linking it up and going through conjugation, we're going to end up making a toxic intermediary where we've just modified the molecule a little bit. We've stripped off an ethyl group, and now we have a reactive molecule. Now, normally, this would only exist for a fraction of a little time period, essentially, and would then get conjugated itself. So it could get turned into something that is non-toxic through GSH glucuronide combination, where we're going to basically take a sulfur-bearing group and we're going to make it into a non-toxic version. But if the body is already working on alcohol dehydrogenation, we can end up with the molecules grabbing on to some of those free protons and electrons and turn it into a compound that can then interact with your cellular proteins that bear sulfurs, and that can then end up disrupting the cells by effectively destroying enzymes, or even worse, starting to destroy cell integrity if it is working on some of the proteins that are helping maintain flow in and out of cells. So this is one of those tricks. Remember, all pathways can go different directions. The body has evolved ways to try to detoxify things, but your cells don't have brains. Your enzymes don't have brains. All they can do is follow the pathways. And in general, it works, but you can have systems where you can end up making toxic compounds by accident through the attempts to detoxify them and burn them as food. So that is in general what I want you guys to know about phase 1 and phase 2. Your text goes into a lot more detail on it. The other thing to remember is these are not just phase 1 immediately followed by phase 2. We can add other phases, and just remember that certain molecules can go through dozens of different steps before they're inactivated and destroyed. So there's a little bit of simplification here, but really it is that same idea. We're either going to modify the molecule by phase 1, like interactions, where we're going to oxidize it, reduce it, have hydrolysis work on it, or we're going to do some kind of conjugation. That's really the big thing. All right, guys, so I will see you next time. Have a great day.